In the vast dark, past every planet you have ever seen, a spacecraft the size of a small car found a wall that should not exist. Scientists expected it to be calm out there, cold, quiet. Instead, Voyager 1 hit a region hotter than anything nearby, patched with fire and ice at the same time, humming with a sound nobody predicted. We built this machine to study planets. It ended up rewriting the edge of the solar system. Ahead, we travel through a boundary that breathes and shifts on its own, a magnetic field that refuses to obey the rules, and a second spacecraft that found something completely different only 6 years later. Every answer Voyager sent back opened 3 new questions. If you want to understand where our solar system actually ends, and what is waiting just past it, stick around and subscribe for more. Prepare yourselves. We begin. A spacecraft the size of a small car slipped past the edge of everything we understand, and for weeks, not a single scientist on Earth realized it had happened. Voyager 1 had been flying since 1977. By 2012, it was farther from home than any human-made object had ever traveled, deep in a region called the heliosheath, the outer skin of the sun's protective bubble. The plan was simple: keep flying, keep sending data back, eventually cross into interstellar space, the vast ocean between stars. On August 25th, 2012, it happened. Voyager crossed the boundary, but there was no flash, no siren, no dramatic signal telling anyone on Earth that history had just occurred. The spacecraft kept humming along, sending its usual stream of numbers back across 11 billion miles of empty space. Nobody flagged it as anything unusual. It took months of careful work before scientists noticed something had changed in the data. When they finally looked closely, the numbers made no sense at first. Something out there had flipped, and flipped hard. Here is why the delay happened. Voyager did not have a sensor that could simply announce, "You have left the solar system." Instead, scientists had to piece the crossing together, like detectives working a cold case, using indirect clues buried in months of transmissions. Imagine trying to figure out you had walked into a new country only by noticing the soil under your shoes had quietly changed color days after you crossed the border. Once researchers dug through the numbers, they found 2 enormous shifts. The particles Voyager had been swimming through for 35 years, particles blown out by the sun itself, had almost vanished. At the same time, a completely different kind of particle came flooding in, particles from deep in the galaxy, particles that had been blocked by the sun's influence for the spacecraft's entire journey. This was confirmed as the moment Voyager 1 became the first human-made object to reach interstellar space. 35 years of flying, and it took months of quiet detective work just to prove it had actually happened. But the story does not end with a simple border crossing. What scientists found once they understood the shift was stranger than anyone expected. The region Voyager had entered was not the calm, cold, empty void that textbooks predicted. It was something else entirely, something that would make researchers question what they thought they knew about the edge of our solar system. Picture the sun as a campfire in the middle of a dark field, its light and heat pushing back the cold night air in every direction. Voyager had just walked past the edge of that firelight, out into the dark. Except the dark was not quiet, it was not still, and it was about to get a lot stranger. Before we go further, it helps to understand exactly what Voyager crossed, and why that invisible line even exists in the first place. Picture standing at a beach where the waves suddenly stop, all at once, without warning. That is roughly what happened to Voyager 1, except the waves were not water, they were particles, streaming from the sun at speeds that would carry them across the entire United States in under 10 seconds. For 35 years, Voyager had been swimming through this constant stream, called the solar wind. Then, within a matter of days, it nearly disappeared. Instruments on board recorded the count of solar particles dropping to a tiny fraction of what it had been just weeks earlier. Scientists had expected this to happen eventually. What surprised them was how fast it occurred, and what rushed in to take its place. As the sun's particles thinned out, a different kind of particle surged in, These were galactic cosmic rays, tiny fragments of atoms blasted across the galaxy by exploding stars and other violent events, sometimes millions of years before Voyager ever caught one. Inside the sun's bubble, these particles are mostly blocked, deflected by the same solar wind that was now fading away. Outside that bubble, they arrive nearly unfiltered. The jump was enormous. Voyager recorded a spike of these deep space particles rising by roughly 25%, arriving almost the moment the solar particles dropped. Two completely different populations, trading places within days, out at the very edge of everything the sun touches. Think of it like a lifeguard leaving a beach right as a storm surge rolls in. As long as the lifeguard, in this case the sun's own wind, is on duty, the beach stays relatively calm and protected. The moment the lifeguard walks away, the ocean takes over completely. This particle flip became one of the strongest pieces of evidence that Voyager had truly left the solar system behind. It was not a guess or a rough estimate. It was a clean, measurable, repeatable signal, confirmed by multiple instruments working independently and agreeing with each other. But the flip raised a bigger question that scientists could not ignore. If the boundary between our solar system and interstellar space was this sharp, this sudden, then what did that boundary actually look like up close? Was it a thin line, crossed in an instant, or was there a wider, messier zone where the two forces fought for control? The particle counts alone could not answer that. They only proved something dramatic had happened. To understand what that boundary actually was, made of, and shaped like, scientists needed a much bigger picture. They needed to understand the sun's bubble as a whole and why it exists at all, stretching for billions of miles into the dark, holding back an entire galaxy's worth of radiation, with nothing but a stream of charged particles. That bubble has a name. Its story starts not at the edge, but back home, at the source of the wind itself. Every model, every prediction, every textbook chapter written before 2012 agreed on one thing. Interstellar space should be quiet, cold, empty, practically silent compared to the churn and storm of activity closer to the sun. That was the expectation Voyager 1 carried with it as it approached the edge of the solar system. Scientists pictured a gentle fade, like a fire slowly dying down to embers, then to nothing. What Voyager actually found broke that picture apart. Instead of a slow, gentle transition, the spacecraft ran into a region packed with unexpected activity. Temperatures spiked far higher than predicted. Magnetic fields behaved in ways nobody had modeled. Particle counts swung wildly instead of settling into the smooth, predictable curve scientists had drawn on paper for decades. One team member described looking at the early data and assuming, at first, that something on the spacecraft itself must be malfunctioning. After 35 years in space, computer glitches and instrument drift were not out of the question, but instrument after instrument kept reporting the same strange story. This was not a broken sensor, this was real. Here is a simple way to picture it. Imagine walking out of a warm house into what you expect to be a quiet, empty parking lot, only to step directly into the middle of a thunderstorm, wind howling, lightning flashing, the ground shaking under your feet. That mismatch between expectation and reality is exactly what scientists experienced reading Voyager's numbers. The region just past the heliopause turned out to be layered, turbulent, and far more dynamic than the smooth boundary shown in old diagrams. Instead of one clean line separating solar system from interstellar space, Voyager found a zone of conflict, a place where two enormous forces pushed against each other constantly, creating pockets of extreme heat, sudden magnetic shifts, and particle storms that came and went without warning. This mattered for more than scientific pride. The heliopause is not just a line on a map, it is the shield that protects every planet, every moon, and every living thing in our solar system from the harshest radiation the galaxy has to offer. Understanding how that shield actually behaves, whether it holds steady or flexes and cracks under pressure, matters for predicting how well it will protect us in the future. especially as the sun's own activity rises and falls over time. So the calm, quiet picture scientists had trusted for decades needed a complete rewrite. The true boundary was not a wall, it was closer to a living, breathing membrane, constantly shifting under pressure from both sides. To understand why that membrane exists at all, and why it puts up such a fight, we need to go back to where it all begins. Not at the edge of the solar system, but at the source of the storm itself, 93 million miles closer to home. The sun is not just a source of light. It is a machine that builds an invisible fortress, one that stretches for billions of miles in every direction. This fortress is called the heliosphere. Picture a giant bubble of charged particles and magnetic energy, blown outward by the sun itself, wrapping around every planet from Mercury all the way past Neptune, and continuing on for billions of miles beyond that. Earth sits deep inside this bubble, protected, without most people ever realizing it exists at all. The bubble is built from something called the solar wind, a constant stream of charged particles blasting out from the sun in every direction at once, at speeds that can reach over 1,000,000 miles an hour. That wind does not just fade into nothing. It pushes outward against the material that fills the space between stars, called the interstellar medium, until the two forces reach a kind of standoff. Think of it like a fire hose aimed into a swimming pool. The water from the hose pushes outward, carving a bubble through the still water around it, until the pressure of the hose weakens enough that the pool water finally pushes back and takes over. The sun's solar wind works the same way, carving a bubble through the galaxy until it runs out of strength and the interstellar medium takes control. That handoff point, the edge of the sun's bubble, is called the heliopause. It marks the true boundary of our solar system, far beyond the orbits of every planet, even beyond distant dwarf planets like Pluto. Voyager 1 had to travel for 35 years, covering more than 11 billion miles, just to reach it. This bubble is not decoration, it matters enormously for life on Earth. Outside the heliosphere, radiation levels from deep space, cosmic rays, run far higher than inside it. The heliosphere acts as a shield, deflecting a significant portion of that radiation before it ever reaches the inner solar system. Without it, the radiation environment around Earth would look very different. And understanding exactly how strong that shield is has real consequences for future missions, from robotic probes to any future human journeys beyond Earth's orbit. For decades, scientists could only guess at the true size and shape of this bubble using indirect measurements and computer models. Nobody had ever flown a spacecraft far enough to check those models against reality. Voyager 1 changed that, becoming the first direct witness to the true edge of the sun's territory. But guessing where the bubble ends is one thing. Actually crossing through its walls is another. Before reaching the heliopause itself, Voyager first had to survive an entirely different obstacle, a violent, turbulent zone that acts like a speed bump the size of a solar system. That obstacle came first, and it nearly shook the spacecraft's instruments apart. Every second of every day, the sun throws away a piece of itself. Not sunlight, something more physical. The sun constantly sheds charged particles, mostly protons and electrons, blasting them outward in every direction at incredible speed. This stream never stops. It has been blowing continuously for over 4 billion years, and it will keep blowing for billions more until the sun itself finally dies. Scientists call this the solar wind, though calling it wind barely captures how strange it actually is. This is not air moving across a landscape. It is raw matter, torn straight from the sun's outer atmosphere, flung into space at speeds that can top 1,000,000 miles an hour. At that speed, a single particle could cross the distance from New York to Los Angeles in under 10 seconds. Here is the strange part. Despite that incredible speed, the solar wind eventually runs out of steam. As it travels farther and farther from the sun, spreading out in every direction, like ripples from a stone dropped in a pond, its density and pressure steadily drop. By the time it reaches the outer edges of the solar system, billions of miles from where it started, that once ferocious wind has thinned into something almost gentle. Picture blowing up a balloon. Near your mouth, the air rushes out with real force. But if you tried to blow up a balloon the size of a football stadium, that same breath of air would arrive at the far walls barely strong enough to be felt at all. The solar wind faces the same problem, except its stadium is billions of miles wide. Eventually, the outward push of the solar wind grows so weak that it can no longer overpower the pressure of the material, filling the space between stars. That is the moment the sun's influence effectively ends and true interstellar territory begins. Understanding exactly where and how that happens took scientists decades of study, and even now, new data keeps forcing them to revise their models. This matters far beyond simple curiosity. The strength of the solar wind directly determines how large the heliosphere becomes, which in turn determines how much protection Earth and the rest of the solar system receive from dangerous cosmic radiation streaming in from the wider galaxy. A weaker sun, over long stretches of time, could mean a smaller shield. A stronger sun could mean a bigger one. The size of our protective bubble is not fixed. It breathes in and out with the sun's own activity. Voyager 1 was built to fly straight through this entire process, from the strong winds near the inner solar system to the faint, fading edges billions of miles out. But faint does not mean smooth. Long before reaching true interstellar space, Voyager had to survive a violent transition zone where the weakening solar wind suddenly slams into resistance, and everything gets rough fast. Long before Voyager 1 ever reached true interstellar space, it had to survive a sudden, violent jolt, the first sign that the sun's power was finally running out. Scientists call it the termination shock. As the solar wind travels outward, thinning with every passing mile, it eventually slows down dramatically and abruptly, the same way ocean waves suddenly pile up and crash as they reach shallow water near a beach. That sudden slowdown creates a shockwave, a rough, turbulent boundary where the smooth outward flow of solar particles gets violently disrupted. Voyager 1 crossed this termination shock back in 2004, long before it reached the heliopause itself. At the time, this crossing was itself a massive milestone, the first direct evidence that the solar wind truly does slow down the way scientists had predicted. Here is a way to picture it. Imagine driving a car at high speed down an open highway, then suddenly hitting a traffic jam, brakes screeching, speed dropping from 70 miles an hour to a crawl within seconds. The termination shock works the same way for the solar wind, except instead of slowing from 70 to 0, the wind's speed drops from over 1,000,000 miles an hour to a small fraction of that almost instantly on a cosmic scale. Crossing this shock did more than just slow the wind down. It also changed the wind's temperature and density dramatically. Particles that had been flowing in an orderly stream suddenly became compressed and heated, creating a turbulent, chaotic region completely unlike the calm flow Voyager had traveled through for decades beforehand. Past this shock lies a wide, sprawling region called the heliosheath, essentially the outermost layer of the sun's bubble, where the slowed, heated solar wind continues to push weakly against the interstellar material beyond it. Voyager spent years crawling through this region, gathering data that helped scientists finally map out the true shape and thickness of the solar system's outer boundary. This mattered enormously for a project that had already lasted decades. Every new milestone Voyager reached proved that its aging instruments, some of them using technology from the 1970s, could still deliver reliable, groundbreaking science far beyond anything their original designers had imagined. NASA engineers had built Voyager to study Jupiter and Saturn. Nobody in the 1970s expected it to still be working and still making history decades later at the literal edge of the solar system. But the termination shock was only the first challenge. Crossing it proved the solar wind was slowing down as predicted. It did not yet prove where the true edge of the solar system actually sat, or what that edge would look like up close. That answer waited years further down Voyager's path. Deep inside the sprawling, turbulent region the termination shock had opened up. That region held its own secrets and its own surprises, long before Voyager ever reached the true heliopause. Past the termination shock, Voyager 1 entered a strange, sprawling region that felt nothing like the smooth solar system it had left behind. This region is called the heliosheath, and it stretches for billions of miles, forming the outermost layer of the sun's protective bubble. Think of it as the thick, worn edge of a soap bubble right before it pops, stretched thin, buffeted by outside pressure, no longer smooth or predictable. Inside the heliosheath, the solar wind that once raced outward at over 1 million miles an hour has already been dramatically slowed by the termination shock. But slowed does not mean calm. Voyager's instruments recorded a region full of turbulence, shifting magnetic fields, and unpredictable pockets of pressure, all fighting against the incoming push of interstellar material from outside. It took Voyager years just to cross this single region. For comparison, the entire distance from the Sun to Pluto could fit inside the heliosheath several times over. This was not a quick trip through a thin boundary layer. It was a long, grinding journey through a genuinely enormous zone of conflict. One of the biggest surprises to emerge from this stretch of the mission involved the heliosheath's thickness. Scientists had built models predicting a fairly specific, uniform depth for this region. Voyager's real measurements told a messier story, revealing a heliosheath far more irregular and unevenly shaped than any model had captured, thicker in some directions and thinner in others. Picture squeezing a balloon between your hands. It does not simply shrink evenly in every direction. It bulges unevenly, thicker where less pressure pushes against it, thinner where the outside force presses harder. The heliosheath behaves in a strikingly similar way, shaped and reshaped by uneven pressure from the interstellar material surrounding the entire solar system. This uneven shape carries real consequences. If the heliosheath is thicker in some directions than others, that means the level of protection our solar system receives from dangerous cosmic radiation is not the same in every direction either. Some parts of the solar system's outer shield may simply be stronger than others, a discovery that reshaped how scientists think about the sun's bubble as a whole, no longer as a perfect sphere, but as something closer to a dented, irregular shell. By the time Voyager finally approached the far edge of the heliosheath, scientists knew they were closing in on something historic. Every signal suggested the spacecraft was nearing the true boundary of the solar system, the line separating the sun's territory from the rest of the galaxy. What Voyager found waiting at that final edge would turn out to be stranger and far more extreme than anything it had encountered inside the heliosheath itself. The heliopause is not a wall you could touch, and it is not made of anything solid at all. It is a boundary built entirely out of a struggle between two invisible forces. On one side, the outward push of the sun's own solar wind, weakened after billions of miles of travel, but still fighting for territory. On the other side, the inward pressure of the interstellar medium, the thin but persistent material that fills the space between stars across the entire galaxy. The heliopause sits exactly where those two forces finally reach balance. Scientists sometimes compare it to the surface tension on a water balloon, an invisible skin holding two different environments apart, without being a wall in any traditional sense. Push from one side, and the skin bulges. Push from the other, and it bulges back. The heliopause behaves in almost exactly the same way, constantly adjusting, constantly under pressure from both directions. Crossing this boundary means leaving the sun's direct influence behind completely. Inside the heliopause, particles blown out by the sun dominate the environment. Outside it, particles born in exploding stars and other events across the galaxy take over instead. It is, in every practical sense, the true edge of our solar system, far beyond the orbits of the planets, farther even than most people ever imagine. The The distance involved is almost impossible to picture using everyday numbers. Voyager 1 crossed the heliopause after traveling roughly 122 times, the distance between Earth and the Sun, a distance so vast that light itself, traveling at over 670 million miles an hour, still takes more than 17 hours to cross it. Here is a comparison that might help. If the Sun were the size of a basketball placed at one end of a football field, Earth would sit just a few inches away. The heliopause, at this same scale, would not even fit on the field. It would sit roughly 2 miles down the road. For decades, scientists could only estimate where this boundary sat, using computer models built from indirect measurements taken from Earth. Nobody had ever measured it directly. Voyager 1 changed that completely, becoming the first spacecraft in history to physically cross this line and send back real data from the other side. What that real data revealed shattered the clean, simple picture scientists had trusted for years. The heliopause was not a smooth, predictable boundary. It behaved more like a living membrane, thickening, thinning, and shifting depending on conditions on both sides. And once Voyager pushed through that membrane, its instruments began recording numbers that no model had prepared anyone for. Numbers that would eventually earn this region a nickname involving fire. The first sign that something extraordinary was happening came not from a single dramatic moment, but from numbers on a screen that simply refused to match anyone's predictions. As Voyager 1 pushed deeper past the heliopause, its instruments kept reporting readings that clashed directly with decades of careful modeling. Temperature sensors recorded values far higher than anything scientists expected to find in supposedly cold, empty interstellar space. Magnetic field sensors detected patterns that broke rules considered almost settled science. Particle detectors picked up combinations that, on paper, should not have been able to exist side by side. At first, some researchers wondered if something had gone wrong with the aging spacecraft itself. Voyager had been flying for over 3 decades by this point, running on technology designed before most of today's smartphones would have seemed like science fiction. A glitch seemed like a reasonable first guess, but the readings held steady across multiple instruments, each one built and calibrated separately, each one confirming the same strange story independently. This was not a broken sensor. This was real data, describing a real environment that nobody had accurately predicted. Here is a comparison that captures the shock involved. Imagine sending a thermometer into what you expect to be a walk-in freezer, only to have it report temperatures closer to a summer sidewalk. That is roughly the scale of mismatch between prediction and reality that Voyager's team faced when they first reviewed this data. The most immediate mystery involved heat. Scientists had built their models around a simple, intuitive idea. As you move farther from the Sun, temperatures should generally drop. Voyager's data flipped that expectation on its head in the region just past the heliopause, recording pockets of plasma heated to tens of thousands of degrees, dramatically higher than the calm, cold conditions that had been predicted for decades. This mattered for more than scientific curiosity. If the boundary of the solar system behaved this differently from every prediction, then every model used to estimate radiation exposure, shielding effectiveness, and even the overall shape of the solar system's protective bubble needed serious reconsideration. Future missions, and any long-term plans for exploring beyond the solar system, would need to account for an environment far more extreme and unpredictable than anyone had designed for. Scientists began digging deeper into exactly what was causing these extreme temperature readings. The answer, once they found it, would reshape how an entire generation of researchers pictured the true edge of our solar system, replacing a quiet, cold void with something closer to a slow, silent inferno stretched across billions of miles of space. That discovery would soon earn a nickname dramatic enough to make headlines around the world. Heat was not the only mystery waiting for Voyager 1 at the edge of the solar system. Its magnetic field readings told an equally strange story. one that struck right at the heart of a theory scientists had trusted for decades. Before Voyager ever crossed the heliopause, most researchers expected a clear, dramatic shift in the direction of the magnetic field once the spacecraft left the Sun's influence behind. Inside the heliosphere, the Sun's own magnetic field dominates everything, twisted and shaped by the constant outward flow of solar wind. Outside it, in true interstellar space, an entirely different magnetic field takes over, generated by forces spread across the wider galaxy rather than by our own star. Scientists expected these two fields to point in noticeably different directions, since they come from completely unrelated sources. Crossing the heliopause, according to this model, should have felt something like walking through a doorway and finding a compass needle swing sharply to point a new way. That is not what happened. When Voyager's instruments measured the magnetic field just outside the heliopause, the direction barely changed at all. The interstellar magnetic field lined up closely with the field the spacecraft had already been traveling through inside the solar system, an alignment nobody had predicted and few could immediately explain. Picture crossing from one country into a completely different country, expecting the language, currency, and customs to change entirely at the border, only to find people speaking the exact same language on both sides. That mismatch between expectation and reality is exactly the kind of surprise scientists faced when they reviewed Voyager's magnetic field data. This alignment raised serious questions about how the Sun's magnetic field and the wider galactic magnetic field actually interact at their boundary. One leading idea suggests that the Sun's own field lines get dragged outward and stretched by the solar wind, reaching into a zone where they can partially blend or connect with the interstellar field beyond, a process scientists call magnetic reconnection. This reconnection can release enormous amounts of energy, transforming the motion of particles into intense heat, possibly helping explain the extreme temperatures found in the same region. The significance of this discovery reached far beyond simple curiosity about compass directions. Magnetic fields play a critical role in deflecting dangerous radiation away from the inner solar system. If the boundary between the Sun's field and the galaxy's field behaves in ways nobody predicted, then models of how well our solar system shields itself from cosmic radiation need serious revision, with consequences for everything from satellite design to future deep space missions. Scientists continued watching Voyager's data for years afterward, waiting for the magnetic field to eventually shift into a pattern matching pure interstellar space. That expected rotation still has not fully appeared, more than a decade after the initial crossing, an ongoing mystery that researchers are still working to solve using newer missions, launched specifically to study this exact question. But the magnetic mystery was only one thread in a much larger, stranger picture forming at the edge of the solar system, one that would soon connect directly to the extreme heat Voyager had already discovered. 10 years is a long time to wait for a compass needle to move. That is essentially the situation Voyager 1's science team found themselves in after the spacecraft crossed the heliopause. Based on established models of how the Sun's magnetic field and the galaxy's magnetic field should interact, researchers expected a clear rotation in field direction within a reasonable stretch of time after leaving the solar system behind. Instead, more than a decade later, that expected rotation still had not clearly occurred. This extended delay puzzled scientists in a very specific way. It was not simply that the magnetic field lined up closely at the moment of crossing. The alignment kept persisting, year after year, refusing to shift into the pattern models predicted for true, undisturbed interstellar space. One possible explanation involves timing and geography rather than any flaw in the underlying physics. Voyager may still be traveling through a transitional zone, a kind of in-between region where effects from the Sun's magnetic field linger longer than expected before finally fading into pure interstellar conditions. Picture wading out of a swimming pool, only to discover the tile deck around the edge stays wet and slippery for much longer than you assumed, an extended transition zone between one environment and the next. If this explanation holds true, It would mean the boundary of the solar system is not a single clean line at all, but rather a wide, gradual transition stretching much farther than anyone previously calculated. That distinction matters enormously for scientists trying to map the true size and shape of the Sun's influence across the galaxy. There is a genuine, unresolved mystery here that scientists openly admit they cannot yet fully explain. Multiple experts studying Voyager's ongoing data have described this lingering magnetic alignment as one of the most stubborn open questions left over from the entire mission, a question serious enough that new missions have been designed specifically to help answer it. This uncertainty carries real weight beyond scientific pride. Understanding exactly where the Sun's magnetic influence truly ends helps researchers build far more accurate maps of the solar system's outer shield, information that matters for predicting radiation exposure on any future missions sent beyond the orbit of Pluto. A boundary that shifts and lingers unpredictably is far harder to plan around than a clean, predictable line. Voyager 1, now traveling farther from Earth than any spacecraft in history, continues sending back magnetic field data more than a decade after its historic crossing, still probing a mystery nobody expected to remain unsolved for this long. But magnetic fields were never the only puzzle waiting in this region. The extreme heat scientists had already discovered nearby was about to earn a nickname dramatic enough to make headlines across the world. Some scientific mysteries resolve quickly, once a new measurement or a clever model fills in the missing piece. This is not one of those mysteries. The persistent alignment between the Sun's magnetic field and the interstellar magnetic field beyond the heliopause has become one of the most closely watched open questions in modern space science. Researchers have proposed several competing explanations, each one plausible, none of them fully proven, creating a genuine scientific puzzle still being actively investigated more than a decade after Voyager first crossed into interstellar space. One leading idea involves the shape of the Sun's magnetic field itself. Rather than a simple, uniform bubble, the Sun's magnetic field forms enormous, sweeping spiral patterns as it travels outward, shaped by the Sun's own rotation. Some researchers believe these spiral patterns might create localized regions where the Sun's field naturally lines up closely with the surrounding interstellar field, purely by geometric coincidence, rather than any deeper physical connection between the two. Another explanation points back toward magnetic reconnection, the same process that may help explain the extreme heat found near the heliopause. If the Sun's field lines and the interstellar field lines are actively merging and exchanging energy at the boundary, that process could naturally pull both fields into closer alignment than models built without reconnection ever predicted. A third possibility suggests Voyager simply has not traveled far enough yet. Under this view, the spacecraft remains within a genuinely transitional region, and the expected rotation will eventually appear, just much farther out than anyone originally calculated. Picture 3 different detectives investigating the exact same crime scene, each one building a completely reasonable theory from the same evidence, yet reaching different conclusions. That is essentially where the scientific community stands today regarding this specific mystery. Multiple credible theories. No clear winner yet. Resolving this question matters, for reasons that stretch well beyond simple curiosity. The exact structure of the boundary between our solar system and the galaxy beyond directly shapes how effectively that boundary protects us from dangerous cosmic radiation streaming in from deep space. A boundary shaped by magnetic reconnection might behave very differently in terms of shielding strength and stability than one shaped by pure geometric coincidence. To help finally answer this question, NASA has invested in new missions specifically designed to study this exact region from multiple angles simultaneously, rather than relying on a single aging spacecraft built decades before scientists even knew this mystery existed. These missions promise to eventually settle a debate that Voyager alone, despite everything it accomplished, has not been able to fully resolve. Until then, the mystery remains open, a reminder that even after crossing into interstellar space and rewriting textbooks along the way, Voyager 1 continues to raise more questions than it answers. And waiting just ahead, connected closely to this same magnetic puzzle, sits an even stranger discovery, one that would eventually earn the nickname Wall of Fire. Nothing about the temperature readings coming back from Voyager 1 matched what decades of careful modeling had predicted. Scientists expected interstellar space to run cold, somewhere in a range that felt consistent with the vast, mostly empty nature of the space between stars. Instead, instruments detected temperatures in specific pockets, soaring to levels between 30,000 and 50,000 degrees Kelvin, a range dramatically higher than anything researchers had modeled for this supposedly quiet region. For comparison, the surface of the Sun itself runs at roughly 10,000 degrees Fahrenheit. The temperatures Voyager detected, once converted, land in a genuinely similar ballpark, an almost unbelievable finding for a region billions of miles from the nearest star, a region everyone had assumed would be closer to freezing than blazing. Here is where the story gets stranger rather than simpler. Despite these extreme temperature readings, Voyager 1 was never in any danger of burning up or suffering damage from the heat. That seems impossible at first. A temperature high enough to instantly vaporize almost anything on Earth, and yet a fragile, decades-old spacecraft flew straight through it, completely unharmed. The explanation comes down to a critical difference between temperature and heat. Temperature measures how fast individual particles are moving. Heat measures how much total energy actually transfers into an object. In the region Voyager crossed, the particles were moving incredibly fast, technically giving them a very high temperature. But there were so few of them, spread across such enormous distances, that almost none actually collided with the spacecraft to transfer that energy. Picture standing in a room with just a handful of scorching hot sand grains flying around, each one moving unbelievably fast, but so few and far between that the odds of one actually hitting you are close to zero. You could technically measure the room as extremely hot based on how fast those grains move, while still feeling essentially nothing yourself. This distinction mattered enormously for understanding what Voyager had actually found. The high temperatures were real, confirmed independently across multiple instruments, but the region was not remotely similar to fire in any traditional sense. There was no fuel to burn, no combustion, nothing resembling flames in the way most people picture them. Scientists needed a way to describe this bizarre combination of extreme temperature and genuine safety, a region hot enough to sound like science fiction, yet harmless enough for an aging spacecraft to fly straight through without a scratch. That description would soon crystallize into a nickname dramatic enough to capture headlines around the world, a name that sounded almost too wild to be real, yet was based entirely on genuine, carefully confirmed scientific data. Scientists needed a way to describe something that sounded impossible, a region at the edge of the solar system hot enough to rival the surface of a star, yet completely harmless to fly through. The nickname they landed on was the Wall of Fire, a phrase that captured public imagination the moment it appeared in headlines. It painted a vivid, dramatic picture, a blazing barrier standing guard at the true edge of our solar system, daring anything that approached it to burn. The name comes with an important catch. This is not fire in any sense most people picture when they hear the word. There are no flames, no smoke, no combustion of any kind happening at the heliopause. The region contains no oxygen, no fuel, none of the basic ingredients required for burning to occur at all. What actually earned this dramatic nickname was raw kinetic energy, the pure speed and motion of charged particles moving through the region. When particles collide or interact through magnetic forces at extremely high speeds, they generate genuine heat, measured accurately at tens of thousands of degrees. That heat is completely real, confirmed by multiple independent instruments aboard Voyager. It simply has nothing to do with traditional burning. Here is a comparison that helps make sense of this seemingly impossible combination. Think about rubbing your hands together very quickly. The friction generates real heat without any fire, fuel, or flame involved at all. Now imagine that same basic principle, particle collisions generating heat through pure motion and energy transfer, playing out across a region of space so enormous that it dwarfs the entire solar system. The reason this heat could not harm Voyager comes back to something covered earlier: the massive gap between temperature and actual thermal danger. The particles in this region move at blistering speeds, but they are spread so thin across such enormous distances that meaningful collisions with any solid object remain extremely rare. Voyager could fly directly through a region hot enough to sound like science fiction and emerge completely unscathed, simply because there was almost nothing there to actually transfer that heat into the spacecraft itself. This discovery reshaped how scientists picture the true edge of the solar system. Rather than a calm, gradual fade into cold darkness, the heliopause turned out to be an active, energetic, turbulent zone shaped by violent collisions and intense magnetic forces working across unimaginable distances. Understanding this region matters for far more than dramatic headlines. It directly affects predictions about radiation exposure for any future missions traveling beyond the solar system, and it forces scientists to reconsider long-held assumptions about how sharply or how gradually our solar system's influence actually fades into the wider galaxy. But the wall of fire was not a smooth, uniform blaze, stretched evenly across the boundary. Voyager's data revealed something even stranger hidden within it: extreme heat sitting directly beside pockets of relative cold, existing side by side in the very same region. The question of why Voyager 1 survived the wall of fire deserves a closer, more careful look, because the answer reveals something genuinely strange about how heat actually works across the vast emptiness of space. On Earth, heat spreads efficiently because the air around us is packed densely with molecules constantly bumping into each other and into anything nearby, transferring energy rapidly in every direction. A hot stove burns your hand almost instantly because billions of fast-moving molecules slam into your skin every fraction of a second, delivering enormous amounts of energy in a very short window of time. The region Voyager crossed works on a completely different scale. Despite blistering particle speeds, the actual density of matter out there remains almost unimaginably thin, closer to a near-perfect vacuum than anything resembling the air in a room on Earth. Individual particles might be moving fast enough to register temperatures in the tens of thousands of degrees, yet they are spread so far apart from each other that a spacecraft could travel for miles without a single meaningful collision occurring. Scientists sometimes describe this as the difference between intensity and quantity. A single spark from a firework carries an extremely high temperature at the exact instant it exists, yet touching that same spark briefly causes barely any harm at all, because so little actual energy transfers in such a short amount of time. Multiply that same idea across the vast, nearly empty stretches of the outer solar system, and you get a region that can register scorching temperatures on an instrument, while remaining almost entirely harmless to fly through. This distinction between temperature and true thermal danger became one of the most important lessons to emerge from Voyager's journey through this region. Without understanding this gap, the Wall of Fire nickname could easily create a misleading impression, suggesting a region so dangerous that no spacecraft could ever hope to survive it. Reality tells a very different story. Voyager flew straight through this scorching region, using nothing more than the same basic construction it had carried since the 1970s. No special heat shielding, no advanced protective technology designed for this specific threat, because the actual threat to the spacecraft's physical structure turned out to be minimal despite the dramatic temperature readings. This finding carries real weight for planning future missions. If scientists had assumed the Wall of Fire posed a genuine physical danger comparable to its nickname, engineers might have designed unnecessarily heavy, expensive heat shielding for any future spacecraft heading in this direction. Understanding the true nature of this heat, intense but sparse, dramatic but survivable, helps mission planners focus resources on threats that actually matter, rather than threats that merely sound frightening. Yet even with this explanation in hand, one deeper mystery remained completely unresolved. If this heat was scattered so thin and spread so unevenly, why did some pockets of the boundary run dramatically hotter than others sitting just a short distance away? That uneven pattern would soon reveal one of the strangest structural features of the entire heliopause. The wall of fire was never a single, even blaze stretched smoothly across the boundary of the solar system. Voyager's instruments found something far stranger, a region broken into patches, scorching heat, sitting directly beside pockets of relative cold, with no smooth gradient connecting the two. Scientists expected temperature to shift gradually across this boundary, the same way the air outside your house cools down slowly as evening turns into night. Instead, Voyager's data showed sharp, sudden contrasts. One stretch of space would register extreme heat, and just a short distance away, conditions would drop noticeably cooler, with no gentle transition in between. This patchwork pattern puzzled researchers almost as much as the heat itself. A smooth, predictable boundary would have been far easier to explain using existing models. A boundary broken into uneven hot and cold zones suggested something more chaotic happening at the edge of the solar system, forces colliding unevenly rather than blending together in a simple, orderly way. Picture a griddle sitting on a stove with uneven heating elements underneath it. Instead of one uniform hot surface, certain spots scorch instantly, while others stay noticeably cooler, creating a checkerboard of temperatures across a single flat surface. The heliopause, based on Voyager's readings, behaves in a strikingly similar way, except stretched across a region of space so enormous that Earth itself would look like a speck of dust by comparison. Scientists believe this patchiness connects directly to the uneven, turbulent nature of the collision happening at the boundary. Rather than a single, clean handoff between the solar wind and the interstellar medium, the two forces appear to clash unevenly, creating localized zones of intense compression and heating right next to calmer regions where the two sides have not yet fully collided. This finding forced another significant update to how scientists picture the true structure of the heliopause. Rather than a smooth, sphere-shaped boundary with predictable properties in every direction, the edge of the solar system increasingly looks like a lumpy, uneven, constantly shifting frontier, closer to a rocky coastline than a clean circle drawn on a map. The consequences reach beyond scientific curiosity. If the boundary protecting our solar system from cosmic radiation is this uneven, then the level of protection Earth receives may vary depending on exactly where the solar system currently sits relative to the wider interstellar environment. As the solar system continues its slow orbit around the center of the galaxy, moving through different patches of interstellar material over thousands of years, this patchwork boundary could shift and change in ways that gradually affect the radiation environment throughout the entire solar system. Voyager could only sample a handful of specific points along this vast, uneven boundary during its brief crossing. To understand the full picture, scientists needed something else entirely, a way to measure the true density and structure of the material on the other side. That answer arrived through an unexpected stroke of luck involving the Sun itself. Sometimes the most important scientific discoveries depend on pure timing, and Voyager 1 caught one of the luckiest breaks in the entire mission just months after crossing into interstellar space. In April of 2013, the Sun let loose a burst of activity, a coronal mass ejection, essentially a massive eruption of charged particles blasted outward from the Sun's surface. This eruption traveled outward for months before finally reaching Voyager 1, far out in interstellar space, long after the initial explosion back near the Sun. When that wave of solar particles finally crossed paths with Voyager, it did something scientists could use directly. It caused the surrounding plasma, the thin, ionized material filling interstellar space, to vibrate, creating oscillations that Voyager's instruments could detect and measure with real precision. Here is why that vibration mattered so much. Scientists already understood the physics connecting plasma oscillations to plasma density. The same way you can estimate how tightly packed a crowd is by how sound waves and vibrations travel differently through it. By carefully measuring the frequency of these plasma vibrations, researchers could calculate, for the first time with real precision, exactly how densely packed the interstellar medium actually was in the region surrounding Voyager. The result confirmed something scientists had suspected but never directly measured. The density matched, closely, what theoretical models had predicted for true interstellar space, offering some of the strongest confirmation yet that Voyager had genuinely left the sun's bubble behind for good. Picture trying to figure out how crowded a stadium is without being able to see it, using only the sound of an announcement echoing through the space. A tightly packed crowd changes how that sound travels compared to a nearly empty stadium. Scientists used a similar principle here, except instead of sound bouncing off people, they measured vibrations rippling through scattered particles spread across billions of miles of space. This discovery mattered for reasons that reached far beyond simply confirming Voyager's location. Understanding the true density of the interstellar medium surrounding our solar system helps scientists build more accurate models of how the heliosphere interacts with the wider galaxy, and how that interaction might change over long stretches of time as the sun's own activity rises and falls across its natural cycles. It also revealed something scientists had not expected. The interstellar medium, once assumed to be almost perfectly empty and inactive, turned out to be a genuinely active, measurable environment, one where distant solar eruptions could still trigger detectable ripples long after crossing billions of miles of empty-seeming space. This single fortunate eruption opened a door that Voyager's team would return to again and again in the years that followed, using plasma vibrations as a reliable tool for studying a region no spacecraft had ever explored before. But this early measurement, dramatic as it was, only captured a single moment in time. Farther out, as Voyager continued its lonely journey deeper into interstellar space, an entirely new mystery was waiting, one involving a sound nobody expected to find at all. Before Voyager 1 crossed the heliopause, most scientists pictured interstellar space as close to a true vacuum, a region so empty it barely counted as containing anything at all. That picture did not survive contact with real data. Once Voyager began measuring the density of the material surrounding it, using the plasma vibration technique discovered through that lucky solar eruption, a very different story emerged. Interstellar space was not empty. It was filled with thin, scattered material, far less dense than anything on Earth, but far more present and active than anyone had expected. Scientists began tracking these density readings continuously as Voyager pushed deeper into interstellar territory. Rather than staying flat and constant, the numbers shifted noticeably over time, rising and falling in ways that suggested real structure within the interstellar medium itself. Not a single uniform fog, but something closer to drifting clouds of varying thickness. Picture walking through what you expect to be an empty, foggy field, only to discover the fog itself has thick patches and thin patches scattered throughout. Some areas nearly clear, others noticeably denser. Voyager found something similar playing out across the region just beyond our solar system, a landscape with real texture, rather than a single, flat, empty void. This mattered because a genuinely empty interstellar medium would behave very differently than one filled with drifting, uneven material. Density affects how magnetic fields travel, how particles collide, and how radiation moves through a region. A crowded interstellar medium, even one still far thinner than anything found on Earth, changes the physics of everything happening at the edge of the solar system. The discovery also carried implications reaching far beyond our own solar system. If the region immediately surrounding the Sun contains this much structure and variation, it raises real questions about what other stars experience at the edges of their own protective bubbles scattered across the galaxy. Our solar system is not floating through a perfectly uniform void. It sits within a specific, textured pocket of the wider galaxy, one with its own local quirks and variations. Voyager's instruments were never originally designed for this kind of long-term density mapping. The mission's original goals, back in the 1970s, focused entirely on studying Jupiter and Saturn up close. Decades later, engineers on Earth found creative ways to repurpose these aging instruments for a scientific mission nobody could have anticipated when Voyager first launched. This ongoing density mapping gave scientists a rough picture of the immediate region surrounding our solar system. But Voyager 1 was not alone out there. A second spacecraft, its twin, was following a completely different path toward the same historic boundary. And what it found would challenge everything Voyager 1 had already revealed. While Voyager 1 pushed deeper into interstellar space, its twin spacecraft, Voyager 2, remained on its own separate journey, traveling in a completely different direction through the solar system. Both spacecraft launched within weeks of each other, back in 1977, but their paths diverged early on. Voyager 2 took a longer, more roundabout route, using flybys of Jupiter, Saturn, Uranus, and Neptune to slingshot itself across the outer solar system, becoming the only spacecraft in history to visit all 4 giant planets up close. By the time Voyager 2 finally approached the heliopause, 6 full years had passed since its twin's historic crossing. This time gap mattered enormously. The Sun operates on an activity cycle lasting roughly 11 years, swinging between periods of intense storms and relative calm. Voyager 1 crossed near a peak in that cycle, when the Sun was highly active and its solar wind blew with real force. Voyager 2 crossed heading into a much quieter stretch, when the Sun's activity had settled down significantly. Scientists expected this difference to matter. A stronger solar wind should push the heliopause farther outward, inflating the Sun's bubble like a balloon filled with more air. A weaker solar wind should let that same bubble settle back inward. Based on this logic, researchers expected Voyager 2 to cross the heliopause at a noticeably different distance from the Sun than its twin had 6 years earlier. There was another major difference in trajectory. Voyager 1 exited through the northern region of the heliosphere. Voyager 2, following its own separate path, exited through the southern region entirely, sampling a completely different section of the boundary. Picture 2 explorers leaving the same city gate years apart, one departing during a massive storm, the other during a calm, quiet season, and each one leaving through a completely different side of the city. Based on those differences alone, you would expect their journeys beyond the city walls to look completely different from each other. This set up one of the most fascinating natural experiments in the entire Voyager mission. 2 nearly identical spacecraft launched together, now approaching the exact same historic boundary from opposite sides of the solar system at completely different points in the Sun's activity cycle, years apart. Scientists eagerly awaited Voyager 2's crossing, expecting it to reveal crucial new information about how consistent or how wildly different the true edge of the solar system might be depending on direction and timing. What Voyager 2 actually found, once it finally crossed, delivered one of the strangest twists in the entire story, a result that stunned scientists in a completely different way than anyone had predicted. When Voyager 2 finally crossed the heliopause in November of 2018, its instruments immediately revealed a boundary that looked nothing like the one its twin had crossed 6 years earlier. Voyager 1 had passed through a thick, gradual boundary layer, a wide zone where conditions shifted slowly over a meaningful stretch of distance before fully transitioning into interstellar space. Voyager 2 encountered something completely different, a thin, sharp boundary, with conditions changing dramatically within less than a single day of travel. This difference stunned researchers who had expected the 2 crossings to look at least broadly similar. Instead, the data painted a picture of a boundary that behaves completely differently depending on exactly where and how a spacecraft approaches it. Picture 2 people crossing the same river using completely different paths. One wades slowly through a wide, shallow stretch of water that gradually deepens over dozens of steps. The other steps off a steep bank directly into deep water within a single stride. Both people cross the same river, yet their experiences look nothing alike Voyager 1 and Voyager 2 experienced something remarkably similar at the edge of the solar system. Voyager 2's crossing also revealed something its twin never detected at all, an entirely new feature scientists began calling a magnetic barrier, a distinct region of unusually strong, compressed magnetic field sitting right at the boundary, playing a significant role in shaping how particles crossed from one side to the other. Voyager 1's data showed no clear equivalent of this feature during its own crossing years earlier. Researchers also found those tricky temperature readings again, and this time they ran even hotter than expected. Voyager 2 measured temperatures in the surrounding interstellar material, reaching between 30,000 and 50,000 degrees Kelvin, significantly higher than the 15,000 to 30,000 degree range that models had originally predicted for this region. These differences forced scientists to abandon any lingering hope that the heliopause might behave as a simple, uniform boundary, consistent in every direction around the solar system. Instead, the true picture looked increasingly like a lumpy, irregular frontier, its thickness, temperature, and magnetic structure varying dramatically depending on exactly where you approached it and when. This mattered for far more than pure scientific interest. If the boundary protecting our solar system varies this dramatically from one direction to another, then any future missions planning to study or cross this region need to prepare for wildly different conditions depending on their specific flight path, rather than relying on a single, one-size-fits-all model built from either spacecraft's data alone. Yet buried within these stark differences sat one number that stunned scientists more than almost anything else. A coincidence so precise that researchers still cannot fully explain it. Despite every dramatic difference between Voyager 1 and Voyager 2's crossings, one single number lined up so closely that scientists still struggle to explain it. Voyager 1 crossed the heliopause at a distance of roughly 121.5 times the distance between Earth and the Sun. Voyager 2 crossed 6 years later, from a completely different direction, during a completely different phase of the Sun's activity cycle, at a distance of roughly 119 times that same measurement. The gap between those two numbers amounts to just a few percent, an almost eerie level of agreement given how different every other aspect of the two crossings turned out to be. This coincidence directly contradicted what scientists expected going in. Since Voyager 1 crossed during a period of intense solar activity, when a stronger solar wind should have inflated the heliosphere outward, and Voyager 2 crossed during a much quieter period, when a weaker wind should have let the bubble settle inward, researchers anticipated a much larger gap between the two crossing distances. Picture inflating two identical balloons using completely different amounts of air, one filled to near bursting, the other only partially filled, and then discovering, when you measure them, that they ended up almost exactly the same size anyway. That is roughly the level of surprise scientists felt studying these two numbers side by side. Researchers have proposed several possible explanations, though none of them has been confirmed as the definitive answer. One idea suggests the heliosphere might respond to changes in solar activity more slowly than models predicted, smoothing out short-term fluctuations over time rather than inflating and shrinking as quickly as expected. Another possibility involves the specific directions each spacecraft traveled, suggesting the northern and southern regions of the heliosphere might naturally balance out certain differences that would otherwise show up more dramatically along a single shared path. Scientists at Johns Hopkins University, who conducted a detailed comparison of both crossings, openly stated they could not yet fully explain this close agreement using current models. That kind of open uncertainty from experienced researchers signals a genuine unsolved puzzle, not a simple gap waiting for an obvious answer. This mystery matters because it directly challenges core assumptions about how predictably the heliosphere responds to changes in solar activity. If two crossings, this different in every other respect, still landed this close together in distance, then current models may be missing some deeper, more stable mechanism governing the overall size of the Sun's bubble, one not yet fully understood. The heliopause was proving to be far stranger and far more resistant to simple explanation than anyone anticipated when Voyager 1 first crossed it back in 2012. And the mysteries were only beginning to compound from there. Among all the differences between the two historic crossings, one discovery stood out as a genuinely new feature of the solar system's boundary, something Voyager 1's own data had never clearly revealed. As Voyager 2 approached the heliopause, its instruments detected a distinct region of unusually strong, compressed magnetic field sitting right at the edge, a feature scientists began calling a magnetic barrier. This barrier appeared to actively influence how particles crossed the boundary, effectively filtering and shaping the transition between the sun's bubble and true interstellar space. Voyager 1's own crossing data, reviewed carefully after this discovery, showed no clear equivalent feature. Its transition into interstellar space had looked comparatively smoother, without the same kind of sharp magnetic compression Voyager 2 encountered years later. This raised an important question. Was this magnetic barrier a permanent, structural feature of the heliopause that Voyager 1 simply happened to miss during its own crossing? Or did it represent something that appears only under specific conditions, perhaps tied to the quieter solar activity present during Voyager 2's journey? Picture two people walking through the same doorway at different times, one during a calm afternoon, finding the door swinging open smoothly, the other during a windy evening, finding the same door slamming hard against a sudden gust. Both people pass through the same doorway, yet their experiences of that threshold look completely different depending on outside conditions at the exact moment they crossed. Scientists suspect this magnetic barrier may connect directly to Voyager 2's location in the southern region of the heliosphere, where researchers believe the surrounding plasma sits more compressed than in the northern region Voyager 1 had traveled through. A more compressed environment could naturally produce a stronger, more concentrated magnetic barrier right at the boundary. This discovery mattered enormously for understanding how particles actually move across the true edge of the solar system. A strong magnetic barrier could act like a partial filter, influencing which particles are allowed through more easily and which face greater resistance, shaping the overall radiation environment on both sides of the heliopause in ways that a smoother, barrier-free crossing would not. The presence of this feature in only one of the two crossings reinforced a growing realization among scientists studying this region. The heliopause is not a single, uniform structure wrapping evenly around the solar system. It varies dramatically from place to place, shaped by local conditions, solar activity, and factors researchers are still working to fully identify. To date, no complete model has managed to explain every observed difference between the two Voyager crossings using a single, unified theory. Researchers continue proposing new explanations, testing them against the growing pile of data both spacecraft have sent home, searching for a deeper pattern connecting these seemingly contradictory results. That search for a deeper pattern soon led scientists to reconsider something even more fundamental: the basic shape of the heliosphere itself. For decades, scientists pictured the heliosphere using a fairly simple mental image: a smooth, round bubble surrounding the sun and every planet in the solar system, evenly shaped in every direction like a giant ball floating through space. The combined data from both Voyager spacecraft has steadily chipped away at that simple picture. Between the uneven thickness of the heliosheath, the dramatically different boundary layers encountered by each spacecraft, and the surprising magnetic barrier found only during Voyager 2's crossing, researchers increasingly suspect the heliosphere is not shaped like a sphere at all. Some current models suggest a shape closer to a windsock or a comet, stretched longer in one direction than another, shaped by the solar system's own motion as it travels through the surrounding galaxy. Here is the basic idea behind this theory. As the sun moves through the wider galaxy, dragging its entire solar system along with it, that motion creates a kind of headwind pushing against the leading edge of the heliosphere, while the trailing edge gets stretched out behind it, similar to how air resistance shapes the tail of a comet streaming away from its head. Picture a boat moving through calm water. Water piles up and compresses against the front of the boat, while a long, stretched wake trails out behind it. Some scientists believe the heliosphere experiences something similar as it plows through the interstellar medium, compressed on the leading side, stretched out on the trailing side. This theory would help explain much of what both Voyager spacecraft discovered. A stretched, uneven heliosphere naturally produces different boundary conditions, depending on exactly where and from which direction a spacecraft approaches it, potentially accounting for the different thicknesses, temperatures, and magnetic structures found by Voyager 1 and Voyager 2 during their separate crossings. Not every scientist agrees on this exact shape, and the debate remains genuinely unsettled within the research community. Some models favor a more rounded shape with only minor irregularities, while others support the more dramatically stretched windsock theory. Without additional spacecraft crossing the boundary from a wider range of directions, researchers currently lack enough direct data to fully settle this question. This uncertainty carries real consequences. The overall shape of the heliosphere directly affects how cosmic radiation reaches different regions of the solar system, and understanding that shape matters for predicting long-term radiation exposure for any future missions traveling toward the outer edges of the solar system, or eventually beyond it entirely. Resolving this question will likely require new tools beyond what either Voyager spacecraft can currently provide. Scientists have already begun turning to other missions and instruments, specifically designed to map the heliosphere's true shape from multiple angles at once, rather than relying on just two single-point measurements taken years apart. But before those newer missions could fully take over this search, Voyager's own data delivered one more unexpected discovery: a shockwave that seemed to ripple backward through the very bubble it had already left behind. Long after Voyager 1 had already crossed into interstellar space, its instruments picked up something that seemed to defy the simple, one-directional story scientists had been telling about the heliopause. Rather than a single, clean crossing followed by calm, steady conditions, Voyager's data revealed evidence of shockwaves, pressure disturbances rippling through the region, sometimes appearing to travel backward relative to the boundary itself, compressing and disturbing the interstellar material Voyager was passing through long after the initial crossing had already occurred. These shockwaves trace back to the same kind of solar eruptions that had already helped scientists measure plasma density years earlier. When the sun releases a powerful burst of activity, that disturbance does not simply stop at the heliopause. It can continue traveling outward, pushing into interstellar space itself, creating ripples and pressure waves that Voyager's instruments can detect long after the initial eruption occurred back near the sun. Picture dropping a large stone into a still pond, then watching the ripples continue spreading outward long after the stone itself has disappeared beneath the surface. The sun's eruptions work in a strikingly similar way, except the pond in this case stretches across billions of miles of space, and the ripples can take months or even years to reach Voyager, arriving long after the original eruption has been forgotten back on Earth. Scientists tracking these shockwaves discovered something particularly interesting when comparing data from both Voyager spacecraft. The shock patterns detected by Voyager 1 looked noticeably different from those detected by Voyager 2, with different strengths, different shapes, and different timing, adding yet another layer of complexity to an already tangled picture of how disturbances move through this region. This ongoing activity proved something important about the boundary of the solar system. Rather than a fixed, unchanging line, crossed once and then left behind, the heliopause and the region surrounding it remain genuinely active and dynamic, continuously reshaped by fresh disturbances, traveling outward from the sun, even years after either spacecraft completed its initial historic crossing. Understanding these shockwaves matters for reasons beyond simple curiosity about wave patterns. Each disturbance offers scientists a fresh opportunity to measure the surrounding interstellar material in new ways, revealing details about density, temperature, and structure that a single, static measurement could never capture on its own. Every new shockwave essentially becomes another data point, another chance to refine an increasingly detailed picture of a region that once seemed impossible to study directly at all. The shock waves also hinted at something scientists had not fully appreciated before: that interstellar space itself carries a kind of memory, responding and rippling in reaction to distant events happening back inside the solar system long after those events first occurred. That growing sense of an active, responsive environment beyond the heliopause would soon lead to one of the strangest discoveries of the entire mission: a faint, persistent sound rising from the depths of interstellar space itself. Buried within years of Voyager, one's data sat a signal so faint that scientists almost missed it entirely, a discovery that would not fully come to light until years after it first began. Starting sometime around 2017, Voyager's plasma wave instrument began picking up something unusual: a persistent, extremely faint signal humming at a steady, narrow frequency. Unlike the dramatic, short-lived bursts triggered by solar eruptions, this new signal did not spike and fade. It simply continued, quietly, consistently, month after month, year after year. At first, this faint signal barely registered as noteworthy. It sat so close to the sensitivity limits of Voyager's aging instrument that researchers needed years of careful, patient analysis before they felt confident enough to confirm it represented something real, rather than simple background noise or instrument drift. Once confirmed, the discovery revealed something scientists had never directly detected before: a persistent, ongoing hum coming from the plasma-filling interstellar space itself, entirely separate from the dramatic shock waves triggered by distant solar eruptions. Picture standing in a room you always assumed was completely silent, then finally noticing, after years of careful listening, a faint, constant hum running underneath everything else, present the entire time, simply too quiet to notice at first. That is roughly the experience scientists had piecing together this signal from years of Voyager's archived data. Researchers involved in the discovery described the signal as remarkably steady, almost like a single, sustained musical note held at an extremely low volume, compared to the much louder, more chaotic bursts triggered by solar storms passing through the same region. This hum offered something genuinely new and valuable: a continuous, ongoing way to measure the density of the interstellar medium surrounding Voyager without needing to wait for a lucky solar eruption to trigger a usable signal. Previously, scientists could only measure plasma density during these occasional, dramatic bursts, leaving long gaps between reliable readings. This faint hum filled in those gaps, offering a steady stream of density measurements collected continuously over months and years at a time. The scientific value of this discovery reached far beyond simple curiosity about a faint sound in deep space. It gave researchers a genuinely new tool for studying the fine structure of interstellar space, revealing subtle variations in density that occasional, dramatic bursts alone could never fully capture. But the discovery also raised an entirely new question that scientists had not fully anticipated. If interstellar space could produce this kind of quiet, persistent signal, what exactly was generating it in the first place? And had anyone actually been searching for something like this before Voyager stumbled onto it almost by accident? The discovery of the interstellar hum did not come from a carefully planned experiment. It came from scientists digging back through years of old, previously overlooked data, searching for patterns nobody had specifically been looking for. A research team, led by an astronomer at Cornell University, set out to find a more consistent way to measure interstellar plasma density. Tired of relying only on rare, unpredictable solar eruptions for usable data, rather than waiting for a dramatic new event, they combed back through roughly 3 years of Voyager's archived transmissions, searching for any weak, consistent signal hiding beneath the instrument's usual background noise. That patient search paid off. Buried within data collected between 2017 and 2020, the team found a faint, narrow band signal appearing consistently far weaker than the dramatic shockwave bursts scientists had studied before, but present steadily across the entire multi-year stretch of data. The signal's origin remains genuinely uncertain, marking one of the more intriguing open mysteries connected to this discovery. Researchers have proposed a few possible explanations. One idea suggests the hum comes from naturally occurring thermal vibrations within the plasma itself, generated simply by the ordinary movement and interaction of charged particles drifting through interstellar space. Another possibility involves subtle electrical fields created by electrons moving through the plasma, producing a kind of background noise similar to static. Picture searching through years of old security camera footage, originally recorded for a completely different reason, only to discover a faint, consistent sound running quietly in the background the entire time, one nobody had specifically been listening for until someone finally thought to check. This accidental nature of the discovery highlights something important about long-running space missions like Voyager. Instruments launched decades ago, designed to answer very different scientific questions, can end up capturing valuable data nobody originally anticipated, simply by continuing to operate far longer than their original mission ever intended. The research team ultimately published their findings in a respected scientific journal, confirming the hum as a genuine, previously undetected feature of the interstellar medium rather than a fluke or an instrument malfunction. This confirmation opened an entirely new avenue for studying the region beyond our solar system, one based on continuous, steady listening rather than waiting for rare, dramatic events. Beyond satisfying scientific curiosity, this discovery reinforced a growing theme running through nearly every chapter of Voyager's journey through this region. Interstellar space, once assumed to be a nearly silent, empty, uneventful place, kept revealing hidden layers of activity that nobody had expected to find. Each new discovery adding another piece to an increasingly complex picture of what actually exists just beyond the edge of our solar system. That steady hum would soon prove useful for something far more practical than simple curiosity, helping scientists track subtle changes in the density of interstellar space over time. Once confirmed, the faint interstellar hum became one of the most valuable tools scientists had for studying the region beyond our solar system, offering a continuous window into an environment that had previously only revealed itself in brief, scattered bursts. By carefully tracking small shifts in the hum's frequency over time, researchers could calculate corresponding changes in the density of the surrounding interstellar plasma, essentially turning Voyager's aging instrument into a kind of ongoing density gauge, reporting steady updates from a region no other spacecraft had ever directly explored. This continuous tracking revealed something scientists had suspected, but never confirmed with this level of detail. The density of interstellar space surrounding Voyager was not perfectly uniform. It fluctuated in small, measurable ways over relatively short distances, revealing genuine structure and texture within material that had once been assumed to be essentially flat and featureless. Picture using a single, sensitive microphone to track subtle changes in air pressure across a room, picking up small variations invisible to the naked eye, yet clearly measurable through careful, continuous listening. Voyager's plasma wave instrument performed a similar function, translating subtle density changes in interstellar space into a signal scientists could carefully track and interpret over time. These density fluctuations connect to a broader concept scientists call interstellar turbulence, the idea that the material filling the space between stars is not perfectly smooth or still, but instead churns and shifts in complex, unpredictable patterns, shaped by forces including nearby stars, ancient supernova explosions, and slow-moving magnetic fields stretching across vast regions of the galaxy. Understanding this turbulence carries real scientific weight. The density and structure of interstellar material directly affects how cosmic radiation travels through space, how magnetic fields behave at the edges of stellar systems, and even how future spacecraft might need to be designed to survive long journeys through this environment. A region assumed to be smooth and predictable requires very different engineering considerations than one known to be genuinely turbulent and variable. The hum also gave scientists a powerful new way to cross-check their other measurements. By comparing density readings calculated from the hum against those calculated from occasional shockwave bursts, researchers could confirm their overall picture of the interstellar medium with far greater confidence than either method could provide on its own. This discovery reinforced just how much value remained hidden within Voyager's decades-old instruments. Technology originally designed in the 1970s, still capable of revealing entirely new categories of scientific data almost 50 years after launch, simply because researchers kept finding creative new ways to analyze the information it continued sending home. As valuable as this hum proved to be, it represented only one piece of a much larger, ongoing story. Voyager's instruments kept detecting strange, unresolved behavior in this region, behavior that extended years beyond either spacecraft's initial historic crossing. Crossing the heliopause did not mark the end of Voyager's strange discoveries. Years after both spacecraft passed into interstellar space, their instruments continued detecting unusual particle behavior that scientists are still working to fully understand. One particularly puzzling pattern emerged involving cosmic rays, the high-energy particles streaming in from across the galaxy. Rather than settling into a simple, steady, predictable pattern once Voyager crossed into interstellar space, these particles showed unexpected variations depending on the direction they arrived from relative to the surrounding magnetic field. Specifically, researchers noticed a clear reduction in certain high-energy particles when Voyager's detector faced a direction roughly perpendicular to the local magnetic field. A pattern scientists call an anisotropy, essentially meaning the particles were not arriving evenly from every direction the way a truly random, uniform source would suggest. Picture standing in the middle of a field during a light, steady rain, expecting drops to fall evenly from every angle, only to notice significantly fewer drops landing from one particular direction compared to all the others. That kind of directional pattern, in raindrops or in cosmic ray particles, suggests some hidden structure shaping how they travel, rather than pure, even randomness. Scientists suspect this pattern connects directly to the surrounding magnetic field's shape and behavior, the same magnetic field that had already surprised researchers by refusing to rotate into its expected interstellar orientation years after both spacecraft's crossings. If the magnetic field itself remains partially shaped by lingering solar influence, that could explain why cosmic ray particles moving along or across those field lines show uneven, directional patterns instead of arriving completely uniformly. This ongoing particle activity, discovered years after either spacecraft's initial crossing, reinforced a critical lesson learned throughout Voyager's entire journey through this region. Crossing the heliopause did not deliver a single, clean, final answer about the true nature of interstellar space near our solar system. It opened up a genuinely complex, ongoing area of study, one still generating new questions more than a decade after Voyager 1's historic crossing. Understanding these particle patterns carries real significance beyond pure curiosity. Cosmic rays pose genuine risks to sensitive electronics and to any future human travelers venturing beyond the protective boundary of the heliosphere. Mapping exactly how these particles move and behave near the edge of the solar system helps researchers better predict and prepare for radiation risks facing any future deep space missions. Multiple extended, unexplained disturbances have continued appearing in Voyager's data throughout its ongoing journey through interstellar space, each one adding another small piece to an increasingly intricate puzzle that shows no signs of fully resolving itself anytime soon. And connected closely to all of this ongoing particle strangeness sat that other lingering mystery, the magnetic field rotation that, more than a decade later, still had not fully occurred. More than a decade after Voyager 1 first crossed into interstellar space, one specific prediction from established models has still failed to come true, an expected rotation in magnetic field direction that researchers continue watching for year after year without success. According to standard models, once Voyager traveled far enough beyond the immediate influence of the heliopause, the surrounding magnetic field should have gradually shifted or rotated into an orientation matching the true, undisturbed interstellar magnetic field, the one shaped by forces spread across the wider galaxy rather than by our own sun. That rotation still has not clearly appeared in Voyager's ongoing data, an outcome that continues to surprise scientists who originally expected this transition to complete within a reasonably predictable time frame following the initial crossing. Picture waiting for a compass needle to slowly settle into a new direction after walking into an area with a different magnetic environment, expecting the shift to happen gradually but steadily over a matter of weeks, only to find the needle still pointing in its original direction more than 10 years later. Researchers have proposed several possible explanations for this extended delay, though none has been fully confirmed. One possibility suggests Voyager remains within an unusually wide transitional zone, a region where effects from the Sun's magnetic field simply linger far longer than models originally predicted, before finally fading into pure interstellar conditions. Another possibility involves the specific direction Voyager traveled, suggesting the northern region of the heliosphere might experience an especially slow, gradual transition compared to other directions around the solar system. This ongoing mystery matters for reasons extending well beyond simple curiosity about magnetic field directions. If the transition zone between our solar system and true interstellar space extends much farther than previously calculated, that changes fundamental estimates of exactly how large the heliosphere's total zone of influence really is, information that matters directly for understanding how far our solar system's protective effects genuinely reach. Scientists studying this ongoing puzzle have been careful to note that many aspects of it remain genuinely unresolved, rather than pretending existing models have already solved a problem that clearly persists in the real data. This kind of honest, ongoing uncertainty represents exactly the kind of frontier science Voyager continues to deliver. More than a decade after most people assumed its most dramatic discoveries were already behind it. Resolving this particular mystery will likely require tools and perspectives beyond what either aging Voyager spacecraft can provide on its own. Fortunately, new missions have already been designed specifically to help finally answer these lingering questions about the true structure of our solar system's boundary with the wider galaxy. Those new missions represent the next chapter in this ongoing story, one that continues directly from everything Voyager has already uncovered. Voyager 1 and Voyager 2 accomplished something no other spacecraft in history had ever done. But even after everything they discovered, both missions left behind more open questions than either spacecraft alone could ever hope to answer. Recognizing this, NASA has developed and launched additional missions specifically designed to study the heliosphere's true structure, using entirely new tools and vantage points, rather than relying solely on two single-point measurements collected years apart from two very different directions. One such mission, called the Interstellar Mapping and Acceleration Probe, uses an entirely different scientific approach compared to Voyager's direct, in-place measurements. Rather than physically flying through the heliopause itself, this newer mission observes the boundary from a distance, using specialized instruments to detect particles bouncing back from the edge of the heliosphere, essentially building an indirect picture of the boundary's overall shape and structure from a single, stable vantage point closer to home. Picture the difference between exploring a cave by physically walking through specific tunnels versus standing outside and using sonar to map the cave's overall shape from a distance. Voyager provided the detailed, up-close experience of physically walking through specific tunnels. Newer missions aim to provide the broader, wider view, mapping the entire structure from outside, filling in gaps that a single physical path could never fully reveal on its own. Combining these two very different approaches offers scientists a far more complete picture than either method could achieve alone. Voyager's direct measurements provide precise, detailed data about specific points along the boundary. Newer, distance-based missions provide broader context about the overall shape and behavior of the heliosphere as a whole, helping researchers understand how Voyager's specific findings fit into the bigger picture. These newer missions specifically target several of the unresolved mysteries already discovered by Voyager, including the true overall shape of the heliosphere, the reasons behind the mysterious near-identical crossing distances recorded by both spacecraft, and the still unresolved question of when, or if, the magnetic field will finally rotate into its expected interstellar orientation. This ongoing scientific effort highlights an important truth about space exploration. A single mission, no matter how groundbreaking, rarely delivers final, complete answers on its own. Instead, each mission builds upon those that came before it, using new tools and new perspectives to fill gaps left behind by earlier discoveries, gradually assembling a more complete picture over years and even decades of sustained effort. Even as these newer missions begin contributing fresh data, Voyager 1 and Voyager 2 continue their own journey, still transmitting data from farther away than any human-made object has ever traveled. Even as both aging spacecraft face a genuinely uncertain future, nearly 50 years after launch, Voyager 1 continues traveling farther from home with every passing second, now sitting at a distance so extreme that even light itself struggles to keep up. As of today, a radio signal traveling at the speed of light, over 670 million miles an hour, takes more than 22 hours to travel from Voyager 1 back to Earth. Send a single command to the spacecraft, and the reply will not arrive back home until nearly 2 full days later, once you account for the signal traveling in both directions. This distance creates real, practical challenges for the mission team back on Earth. Every single command sent to Voyager must be planned with extreme care, since there is no way to quickly correct a mistake once a signal is already on its way. A simple error that might take seconds to fix on a nearby spacecraft could take days to identify and correct on Voyager, given the enormous communication delay involved. Picture mailing a letter to a friend, knowing it will take nearly a full day just to arrive, and another full day for their reply to make its way back to you. Then imagine that exact same delay applying to every single command sent to control a 50-year-old spacecraft, flying through one of the most extreme environments humanity has ever attempted to study directly. Power presents an even greater challenge than distance alone. Voyager 1 runs on a radioisotope thermoelectric generator, a device that converts heat from slowly decaying radioactive material into usable electricity. This power source has been gradually weakening since launch, losing a small percentage of its total output every single year, a slow, steady decline that engineers have been carefully managing for decades. To stretch the mission as long as possible, engineers on Earth have been forced to make difficult decisions, gradually shutting down individual instruments and systems one by one, prioritizing whichever instruments still deliver the most valuable scientific data given the spacecraft's shrinking power budget. Several original instruments, still functioning perfectly well, have already been permanently switched off, simply to conserve enough power to keep other, higher priority instruments running longer. This careful, ongoing power management represents one of the most remarkable aspects of the entire mission. Engineers who worked on completely different projects decades ago now devote real time and effort to keeping a 50-year-old spacecraft alive, squeezing every last useful measurement out of instruments that were never expected to still be operating this far into the mission. Despite these mounting challenges, both Voyager spacecraft continue transmitting valuable scientific data from farther away than any human-made object has ever traveled. A remarkable achievement considering their age, their distance, and the increasingly limited power available to keep them running. That achievement will not last forever. Eventually, both spacecraft will fall permanently silent, closing one of the most remarkable chapters in the entire history of space exploration. Every spacecraft mission eventually reaches an end, and Voyager 1 and Voyager 2 are no exception, even after nearly 50 remarkable years of continuous operation. Engineers currently estimate that both spacecraft will run out of enough power to operate any remaining instruments sometime around the year 2025 to 2030, a range based on the steady, predictable decline of their radioactive power sources. Once power drops below a critical threshold, each spacecraft will no longer be able to run its instruments, transmit data, or even maintain contact with mission control back on Earth. This does not mean either spacecraft will simply stop existing or come crashing back down anywhere nearby. Voyager 1 and Voyager 2 will continue drifting silently through interstellar space indefinitely, carried forward by the same momentum that has propelled them since their original planetary flybys decades ago. Long after their instruments and radios finally go dark, picture a message in a bottle, tossed into an ocean so vast that the bottle will likely drift for millions of years without ever reaching another shore. Both Voyager spacecraft will continue a similar journey, silent and dark, carrying humanity's story outward into the galaxy for an almost unimaginable stretch of time. Each spacecraft carries a special object designed specifically for this eventual silence, a golden record containing sounds, images, and messages representing humanity and life on Earth, created in the unlikely event that another intelligent civilization somewhere in the galaxy might one day intercept either spacecraft and wonder who sent it. Scientists do not expect Voyager to encounter another star system anytime soon, at least not on any timescale relevant to human history. Current calculations suggest it will take tens of thousands of years before either spacecraft passes anywhere near another star, and many more years beyond that before any close encounter with another star system becomes even remotely possible. This eventual silence will not erase everything Voyager has already accomplished. Decades of collected data, an actual physical crossing into interstellar space, and years of ongoing measurements from a region no other spacecraft has ever directly explored. All of that scientific legacy will remain permanently available for researchers to study for as long as human civilization continues asking questions about the universe. Even now, as engineers carefully manage the final years of both spacecraft's operational lives, teams back on Earth continue analyzing decades worth of archived data, searching for additional patterns, connections, and discoveries still hidden within transmissions collected years or even decades earlier. The story of Voyager's journey to the true edge of the solar system, and everything strange it found waiting there, does not end simply because the spacecraft themselves will eventually fall silent. It continues in every scientist still poring over their data, and in every future mission built specifically to answer the questions Voyager first raised. Nearly 50 years after launch, two small spacecraft built with 1970s technology continue transmitting real, groundbreaking data from farther away than any human-made object has ever traveled. What began as a mission to photograph Jupiter and Saturn up close turned into something nobody involved in the original 1970s launch could have fully predicted, a decades-long journey that ended up rewriting fundamental assumptions about the true edge of our solar system and about the strange, active region waiting just beyond it. Every major discovery covered across this entire journey, the sudden particle flip marking the true crossing, the extreme heat earning the nickname Wall of Fire, the magnetic field that refuses to rotate as predicted, the strange, persistent hum rising from interstellar plasma, the wildly different boundary layers found by each spacecraft, and the impossible coincidence in crossing distance connecting them. None of it was ever fully expected by the scientists who first designed this mission. Picture setting out on a short road trip, only to discover, mile after mile, an entirely unexpected landscape unfolding ahead of you. Each new stretch of road revealing something stranger and more surprising than the last, far beyond anything the original map ever suggested. That captures, in a small way, exactly what happened as both Voyager spacecraft pushed steadily outward, transforming a planetary mission into humanity's first direct exploration of true interstellar space. The heliopause, once imagined as a simple, calm boundary separating our solar system from the rest of the galaxy, turned out to be something closer to a living, breathing frontier, uneven, unpredictable, and still only partially understood even after both spacecrafts' historic crossings. New missions are already following in Voyager's path, building on everything these two aging spacecraft discovered, aiming to finally answer questions Voyager itself was never equipped to fully resolve. Yet even as those newer missions begin collecting fresh data, nothing will ever replace the historic significance of being first, of physically crossing a boundary nobody had ever directly measured before, and returning proof that the true edge of our solar system looked nothing like anyone expected. Every mile, Voyager 1 and Voyager 2 continue traveling, adds new data to an already remarkable scientific legacy, one that will likely keep generating fresh insights and fresh questions for years after both spacecraft eventually fall silent for good. Two machines, launched during a decade defined by rotary phones and black and white television sets, continue reporting back from the true frontier of human exploration, a place still being mapped, still being understood, and still capable of surprising even the scientists who have studied it most closely for decades. The edge of our solar system is no longer a line on an old diagram. It is a living, ongoing story, and Voyager is still writing it.